Hello class, welcome back. Today I'm going to be going over chapter 8. And chapter 8 just talks about static electricity and current electricity. Alright, so basically in this lecture here, I'm going to be going over electric charge, Coulomb's force, electric field, electric potential, voltage sources, electric current, electrical resistance, Ohm's law, electric current, and electrical power. All right, so let's get right into it. All right. So of course, the first thing I'm gonna go over here is the electric force. The electric force. Now, electricity is something that we all kind of have a good idea of what it is, kind of, and how it works, kind of. Like, we know electricity basically powers everything around us, from our cell phones to our laptops. And if it wasn't for electricity, we wouldn't have things like the internet, cell phones, satellites, or any of that. So I'm sure everyone kind of has a good kind of idea of what electricity is, but we're going to go a little bit deeper into it here, what it is, what causes it, and, all that good stuff. So starting with electric force, the first thing, obviously, you need to know about electric force is that what opposites attract and likes repel, right? Opposites attract and likes repel. Well, opposite what exactly? Well, opposite charges attract, right? And then like charges repel. And so that attraction and that repelling is a force, right? Because we know a force is a push or a pull. So an attraction would be a pull, so it must be an electrical force, and a repel is more of a push. So that's also governed by the electrical force. So let me draw it out here. If I have basically two charged objects, so this object is positively charged. Let's say I draw another positively charged object here. This one's also positively charged. So since both of these objects are both positively charged, where charge is basically, well, we actually don't know what charge is exactly, but we do know charge is like a fundamental thing, kind of like mass. So everything, in the universe has some mass to it, right? So likewise, everything also has some charge to it. So we think of charge as kind of like an inert quality, something that an object just has, so an object just has mass, right? So like this here, this just has mass because it's an object. So likewise, object also has some charge, but usually most objects that are massive like this are neutral, so we don't actually feel any electrical forces coming from it. But let's say these two objects have some charge. They're both positively charged. And so since both of these objects are positively charged, they're going to repel, right? So they're going to basically push away from each other. And so the electrical force on both of these is going to be pushing away like this. Boom. Now, again, so force we know is a interaction, right? So basically these two objects are interacting with each other through their, what we call their electric field, which I'll talk about that in a moment. But basically that one interaction is given by two forces in opposite directions. And so basically this charged object is pushing on that one that way, and this charged object is pushing on this one in the opposite way. All right. So that'd be the same case even if both our objects were negatively charged. Boom. Now, if we have two objects that are opposite, right, we know they're going to attract. Boom. So these two objects, since they're oppositely charged, they're attracted towards each other. So I would probably draw the force lines like this. So this one is attracted that way. And then this one is attracted that way. Because they're attracted to each other. All right? So I think that all that kind of makes sense. I think we've all kind of not necessarily experienced this, but we kind of already have an innate idea in our mind that opposites, attract and like charges repel. All right, so now let me give you what the electric force is. Let me give you the equation for that. So the equation for electric force is given by, we use the F for force with a lowercase e. It's given by K charge 1, charge 2 divided by the distance between them squared. So what does that equation look like? Well, that looks just like the universal gravity equation, right? Well, the universal gravity equation was given by, boom, this. So notice how similar these equations are. Well, we have basically charge 1, charge 2, mass 1, mass 2, divided by their distances squared. And then each of them have some constant, where this is the constant associated with gravity, and then this is the constant associated with electrical force. But the only difference here is that the electric force can either be attractive or repulsive, right? Because charges can be either plus or minus. Whereas masses can only be positive. You can only have a positive mass. You can't have a negative mass. Whereas charges, you can have negative charges and positive charges. And so the main difference between these two here is the electric force can be repulsive and attractive, whereas the gravitational force is only attractive. So the gravitational force is only attracting things towards each other, whereas the electric force can attract things towards each other and push them apart. And that's just because the charges can either be plus or minus. All right. So what carries these positive and electric charges? Well, of course, we have these things called atoms, and we know atoms are made up of things like protons, electrons, and neutrons. Well, it's those little quantities, those atoms. So if I were to draw an atom here, this is my atom. This is the nucleus of the atom. Then this atom has some electrons kind of flying around it like this. So atoms are made up of electrons, which are negatively charged, also made up of protons, which are positively charged, then also made up of neutrons, which, as you can guess, are neutral. They have no charge. So I'll just do a 0 for that. So protons and neutrons basically make up the nucleus, and then electrons make up the outer shell of the atom. The outer shell of the atom. Right? So basically, electrons are what carry the negative charge, protons are what carry the positive charge, and neutrons, since neutrons are neutral, they don't interact with protons or electrons through the electrical force. Because in order for things to interact electricity-wise, they have to have some charge. And since a neutron has no charge, it's not gonna be affected by the negative or positive charges of a proton or electron. Okay, so now let me show you how we draw the electric fields for these electrons and protons. So if we have something, so now I'm going to do the electric field. Electric field. If we have an object that is negatively charged, it's just kind of floating there by itself in space, this object has some electric field associated with it, meaning that around it is some type of invisible field that we can't see, but we know it has, and that field looks like, we draw it like this. These are called electric field lines, and they basically just go outwards in every direction, right? And for a negative charge, they always point towards it. Boom. And similarly, if we have something that's positively charged, it also has an electric field, right, going in all directions, really similar to this one. And for the positive, the electric field lines are going to point away. So here they point away, and here they point towards. Boom. And that's basically how we draw the electric field for, say, a positive charge and, say, a negative charge. Now, if we want to draw the electric field for both of these together, so say we have this negative and this positive charge next to each other, then basically all we'd have to do is kind of connect these field lines. So then we would have basically it going this way, and notice how it's pointing in that direction. And then maybe one more like this. Boom. So then this is how the electric field interaction would look for a positive and a negative charge near each other. And then these outside ones would still kind of look the same. They would just go outwards in their directions. Right. And then I guess the next thing I want to say about these electric field lines, besides the fact that the positive electric field lines point away, the negative electric field lines point towards, another thing you should notice is the spacing between the electric field lines. So basically, the closer the field lines are spaced to each other, the stronger the electric field is in that region. So let me see if I can, well, let's use this as an example. Actually, I'm gonna draw it over again. let's use this. Let's just use one charge for now. So we've got this negative charge. This is what its electric field looks like. Boom. So if I were to draw a dotted line right here, so say we want to know the electric field, and at that point there, well, notice when for this circle here, into this dotted line that I drew, the electric field lines are kind of close to each other. That means the electric field is going to be basically kind of big the closer you get to the source, right? So the closer you get to the source, the stronger the electric field, right? So let's say I want to find the electric field way out here. Well, way out there, notice way out here, the spacings between the electric field lines are actually way bigger. So since the spacings are bigger out here, that means the electric field is going to be weaker. All right, so that makes sense. The further you get away from this source, the less the electric field is going to be. The closer you get to this source, the greater the electric field is going to be. And that basically just depends on how close the electric field lines are to each other. All right, so now that I've kind of shown you the visual for the electric field, let me give you the equation. So the equation for an electric field is given by K Q divided by D squared. So notice that's very similar to the electric force as given by that. Boom. So the only difference between the electric field and the electric force is the electric force has charge 1 and a charge 2, whereas the electric field only has one charge. So why is that? Well, the electric field is only talking about the one object. So we can have just one object by itself. So we can have this one object by itself. All right, and this, let's say this is some charge Q. So this one object by itself has an electric field, but there is no electrical force happening because there's no other charge, right? There basically has to be two objects, right, for there to be some type of interaction. If there's one object by itself, then there's no interaction. Since there's no interaction, there's no force. But as soon as we bring another charge, let's say another charge here, then these two charges, so then this would be 1, this would be 2, these two charges can interact with each other, meaning these two charges will apply some force on each other given by this equation. So that's why the force equation has two charges, whereas the electric field equation only has the one charge. Cool. And then another way we can actually write the electric field is like this. We can also write it as the electric force divided by the charge. All right. So let's see what's next. Looking at these charges, or looking at the slides here. All right, so we've gone over electrical force, electrical charge, electric fields. Okay, so now let's go over conductors and insulators. Conductors and insulators. So basically a conductor is an object right here. A conductor is basically an object that allows electrons to flow or kind of move throughout the material. And then an insulator is basically the opposite. An insulator does not allow its electrons to move freely. Doesn't allow electrons right here to flow. So insulators don't allow electrons to flow, while conductors are objects that allow electrons to flow. So what do I mean by that? Well, basically kind of what I just shown you based off of how an atom is structured, right? An atom is structured with its electrons on the outside. So let's say here's the nucleus, and we have some electrons out here. So this is some atom. So the inside of the nucleus here can't necessarily move too freely, but the electrons out here can move freely for a conductor. So a conductor would be like a metal or most metals, and an insulator would be something more like rubber or wood or something like that. Similar to how we had conductors and insulators for the last chapter when we were talking about thermodynamics and heat. All right, so basically conductors are good because, so let's say we have a wire now. If we have a wire, it's just some wire. And this wire has those atoms inside of it, and the electrons can basically move around inside of this wire. So if we can cause the electrons to move inside of this wire, then we can get some current to flow through this wire. So that gets us right into electrical charge. But I guess before I talk about electrical charge, I skipped the slide here. So let me go over that slide real quick, called polarization. Polarization. And I skipped that slide. So polarization just means the ability for the charges inside of an object to shift left or right. So let's say we have a balloon, right? I think everyone's done something like this. Say you have a balloon. And you rub this balloon on a shirt. So I take this balloon, I rub it on his shirt, As I rub this balloon onto that shirt, this shirt is basically losing electrons. So the electrons on this shirt then get pulled onto the balloon. So let me draw like this. So now the electrons on the shirt get pulled onto the balloon, right? So then now the balloon has some net negative charge. And now the shirt has some net positive charge because it lost its electrons. So if you lose electrons, you become more positive, right? But if you gain electrons, you become more negative. So since the balloon gained electrons, it became more negative. And since the shirt lost electrons, it became more positive. So once you rub this balloon onto this shirt, now these objects now have an opposite charge, right? This balloon has an overall negative charge. This shirt has an overall positive charge. So now after you rub this balloon on your shirt, balloon picks up some charge. Now this balloon is going to be attracted to the shirt and will actually even stick to the shirt, right? So now polarization is just when the charges in that object move around. So let's say, now take this balloon, I put it next to the wall. Let's say this is the wall over here. And this wall is neutral, meaning it has an even amount of positive and negative charges. So it has some positives, but it has an equal amount of negatives. So overall, the wall is neutral. So now if I take this balloon and I put it next to the wall here. So if I take this balloon, put it next to the wall, since this balloon is overall negative, the negatives from this balloon are going to cause some of these positives to be attracted to the balloon. So then the positives are going to kind of build up wherever the balloon is. So this shift of charge here is kind of what we call polarization. So let me do another example of polarization, and maybe it'll make a little bit more sense. So let's say I have this conductor here, and this is the solid part and the inside is empty. So this conductor is neutral. It doesn't have any charge. It just has a balanced amount of positive and electric charge. So I have this conductor, and when I say it's a conductor, that means basically these charges can kind of move around. So now let's say I have this conductor and I move a charged object near it. Let's say I move a positively charged object near it. Say I have some ball, and this ball is positively charged. Once I move this positively charged object near this conductor, what do you think is going to happen to the charges inside of this conductor? Well, since this is positive, it's going to pull the negatives closer to it, right? Because opposites attract. But then also the like charges repel, so it's going to push the positives along the back end. Boom. So once I pull this positive charge object near this conductor then becomes polarized, because now the majority of the positive charges are on this end and the negative charges are on this end. And then also even on the inside here, because this inside is empty. So on this surface, it's actually going to pick up a little bit of negative or positive charge. And then on this surface, it's going to pick up some negative charge. Because these positives are going to be attracted to those negatives, just how these negatives are going to be attracted to that positive. All right, so I hope that makes sense. Okay. So now let me get into electric potential energy. I hope I'm not all over the place here. This chapter might be kind of one of the harder chapters. But, you know, again, just take your time with it. Read over the chapter when you can. And yeah, just remember, these are concepts that people have studied over hundreds of years, and you're trying to learn it within a couple days. So don't be too hard on yourself. Now, let's talk about electric potential energy. So in order for me to describe this, well, let me just describe it in words first. Electric potential energy is basically the energy possessed by a charged particle due to its location in an electric field. Boom. So the electric potential energy is the energy possessed by a charged object because of its location in an electric field. All right, so now let me try to describe that with the diagram. So let's say I have two plates here. I think this is the best way to describe it. So I have two plates here, and this plate has some positive charge. And then this plate up here has some negative charge. Boom. So if I want to draw the electric field between these plates, how would that look? Well, we know the electric field always it points away from positives, right? And towards the negative. So the electric field is going to be pointing upwards like this. That's the electric field. So between these plates, the electric field is going to point from the positives towards the negatives. All right. So now, if I were to put let's say an electron up here. If I put an electron up here. So if I put it up here and I'm just holding it, this electron basically is going to be pushed away from the negative side, right? Because like charges repel, and it's going to be attracted to the bottom side here because it wants to be next to its opposite. So this electron is going to experience some electrical force pulling it downwards. So the fact that this electron is up here, and let's say I'm holding it, right? It has some potential energy, because once I let it go, it's going to basically fall, kinda, but more so really be attracted downwards to the positive plate. So basically, this electron has some potential energy due to the electric field because of where it's at up here. Now, let me give you an analogous scenario that you probably better understand at this point now. Let's say this is the ground. No, regular day life, this is the ground. And we have some rock up here. This is a rock. So if we hold this rock up here at this height, we know this rock is going to have some potential energy, right? Because once we let this rock go, it's going to fall down or be attracted downwards by the force of gravity, and then basically be pulled down to the ground. So similarly, just how like we have this rock above the ground, so it has some potential energy, then this electron, since it's above this positive side, or because it's placed here in this electric field, it also has some potential energy. Okay. So I hope that makes sense. I think that's the best way I can kind of describe it here. And so here, the potential energy we know is given by, here, potential energy is given by mass times gravity times the height, right? And here, the potential energy is given by the charge of that times V, which is V is what we call the electric potential, not the potential energy, but the electric potential. So V equals the electric potential, not the electric potential energy, just the electric potential. And this is measured in volts. Just to kind of give you an idea. So let's talk about that electric potential a little bit. Then I'm gonna go back to potential energy and all that. So hope that makes sense. So now, electric potential energy, or electric potential, I should say, is given by the electric potential energy per charge. So basically, so this is potential energy electric. Well, yeah, it's given by the electric potential times the charge or maybe I should write it like this, VQ. Yeah, so the electric potential energy is given by the potential, the electric potential V, which is measured in volts, times the charge Q. And I think I also forgot to mention that charge is measured in coulombs. So let's see, let me write out the units here. Units for charge are coulombs, and we use a C to abbreviate that. And electric potential is measured in volts, and we use a V for that. So basically, whenever a charge is inside of some potential, inside of some electric potential, it then has the ability to basically move, right? So going back to the parallel plates. And see, there's our electron there. So because this electron is between these plates where there's a electric potential, let's say it's an electric potential here, and let's say let me actually draw it this way. Draw it this way. And let's put a positive charge up here. All right, so now that we have a positive charge up there, this positive charge wants to be pulled downwards, right? And between here is some electric field. Well, let's say between this electric field, there's also an electric potential. So let's say down here is 0 volts. 0 volts. And let's say up here is 5 volts. And so now we can find the potential energy of that charge. This has some charge Q. Potential energy is going to be equal to the voltage times the charge. And so up here at the very, very top, the voltage is 5. Then as this drops downwards, the electric potential gets less and less and less until it reaches 0. And so the potential energy would be basically 5 times Q, whatever that charge is. All right, so now let's talk a little bit more about this voltage or electric potential, which we also call voltage. So a voltage source would be, so what's the source of an electric potential? So a voltage source would basically be something like a battery. Right? Because usually we know we have batteries like AAA, AA, D, all that. And then those batteries have different voltages associated with them. And so a battery has a certain voltage, right? So now let me kind of draw that out here. Let's say I draw a battery. This is my battery. And this is the negative end. This is the positive end. So this battery has some voltage or some electric potential, right? So now, if I were to connect this battery to a conductor, right? Because we know a conductor basically is some material or metal that allows electrons to flow. Boom. So now you can kind of imagine the electrons in this wire are going to be basically pushed away from this positive end. Well, actually, the the electrons are going to be pushed away from this negative end. So the electrons get pushed away from this negative end and go towards the positive end. Boom. So because of this voltage source, because of this battery, or this potential difference, or electric potential, I'm just saying it in different ways, but you know, just different words they would probably use to describe what's happening here. So you could say either this battery or this electric potential or this potential difference is causing electrons to basically flow or kind of fall through this wire here, because the electrons are going to be pushed away from the negative end, right? And they want to be attracted to the positive end. And so this battery is causing a current now. It's causing a current to flow through this this wire. Now, I know I drew the direction this way, which is true. The electrons are going in this way. But since electrons have a negative charge, we usually say the direction of the current is opposite. And we use I for current. So we usually say the direction of the current flows from high to low, or from positive to negative. But, you know, physically what's happening is the electrons are flowing the opposite way, but we always label the current going opposite to the electrons. Cool. So I hope that makes a little bit of sense. So that gets us now into electric current. And so the equation for electric current now that I'm going to give you is called Ohm's law. Ohm's law, which says the potential difference, or the voltage V, is equal to I. This is the voltage. Voltage measured in volts equals I, which is the current. And the current is measured in amperes. Amperes. How you spell that? I think it's amperes, something like that. We usually use A to shorthand it. And so voltage equals the current times what? Times the resistance, R. So R is the resistance. And that's measured in this guy's name's ohms. And we usually abbreviate that with this symbol. So we have the voltage, or the potential difference, is equal to the current that's going to flow through that wire times R, which is the resistance that's in that wire. Well, R is measured in ohms, the current is measured in amperes, and the voltage is measured in volts. So just to give you a quick example of how that works. So this is how we draw our circuit diagrams. Boom. Where this here is the battery. Well, the battery is what's supplying the voltage source, right? So this battery has the voltage source. And then the squiggly line here is what we call our resistor. Resistor. So now, whenever you're dealing with currents, it's always good to kind of think of it as, you know, think of it as like water flowing through a river, or water flowing through a hose of some sort. Even though it's not exactly behaving that way, it's good to kind of keep that picture in mind to better, help these current diagrams make more sense. So you can imagine I drew this bigger line. This bigger line usually represents the positive end. So this represents the positive end. The smaller line represents the negative end. And so we always say the current flows from high to low, so it goes out of the current goes out of the positive end, and then it wraps back around into the negative end. So let's say the voltage, let's say we know the voltage is equal to 10 volts, and we know the resistor R is equal to 2 ohms. What would be the current through this wire? What would be the current? Well, of course, we would just use our Ohm's law, right? Well, Ohm's law says the voltage equals the current times the resistor. And we're trying to find the current, So the current is going to be given by I equals V divided by R. And so the voltage is 10. So it's going to be 10 divided by the resistance, which is 2. So the current's going to be 5. Boom. So kind of quick and easy example of how we use Ohm's law within a circuit. Okay. Let's see, just looking through the slides. All right, so now let me go over a few more current diagrams, some other ways we can set up these currents or these circuits. So there's 2 ways we can set up a circuit. There's 2 ways. We can set up a circuit in series, or we can set up a circuit in parallel. Let me use different colors. Series or parallel. This would be a circuit in series. So we got our battery here. And let's say this resistor is our light bulb. Boom. So notice how there's basically only kind of one line going through this circuit here with 2 light bulbs. And these light bulbs are basically indicating our resistors. And so this has some resistance R, this has some resistance R, and here's our voltage V over here. So for a circuit in series, the resistance is greater, or the resistance adds up. So for a circuit in series, resistance is greater, or in other words, it adds up. All right. So basically what I mean by greater resistance is if we add more and more light bulbs, the current's going to be less and less because the resistance is going to be greater and greater. So we can kind of imagine, now let's say we have 1 light bulb first. And this light bulb shines really, really, really bright. Boom. Light bulb shines really, really bright. Well, if I add that same light bulb over here, if I add another one, then this light bulb is gonna be not shine as bright. It's gonna shine a little bit less. And now this one's gonna shine a little. And so it becomes less bright because there's a greater resistance now. And so now if I also add another light bulb, let's say over here, add a third light bulb, then both of these are going to become a little bit dimmer. Then this one's also going to shine a little bit. So basically, as we add more and more light bulbs in series, then they become less and less bright because the resistance is greater and greater, or the resistance adds up. So that's for a circuit in series. Now, let's do a circuit in parallel. So a circuit in parallel basically does the opposite. So I have to draw this circuit a little bit different to show. Boom. So notice this circuit is in parallel. I'm gonna actually put it in blue for parallel. Draw this one more time. Boom. So this circuit is in parallel because the light bulbs here are each parallel to each other. And so this circuit's in parallel. So whenever a circuit is in parallel, the resistance, the overall resistance, is less. So for circuits that are in parallel like this, the overall resistance gets less and less the more bulbs we add in parallel. So what's that mean for these bulbs here? Well, let's say I only have one bulb. Like this, right? And it's shining, you know, kind of bright. Like that. So let's say I now add another light bulb in parallel. So if I add another light bulb in parallel, the resistance is going to be less, or the resistance is going to decrease. So what do you think is going to happen to the brightness of that bulb? Well, it's actually going to become even brighter because the overall resistance has decreased. And then similarly, if I were to add a third one here, then the brightness would also increase for both of these. Because as I add more light bulbs or resistors in parallel, the overall resistance becomes less and less. So that's series and parallel circuits. So now the last thing, or the last equation I'm going to give you is electrical power. Electrical power, or power, P, which is in watts, right, is given by the current, I, which is measured in amps, times the voltage, V, which is measured in volts. Boom. So this is our equation for power. So power equals the current times the voltage. Not to mix it up with Ohm's law. Which is voltage equals the current times the resistance. So this is the last equation. And let's see, a quick example would be, say we have a light bulb. A light bulb that draws 100 watts of power. And the current going through the light bulb is, let's say, 5 amps. Then what is the voltage? Well, we know power equals I times V. So to find the voltage, we'll take the power and divide by the current. And so it's going to be 100 divided by 5. So the voltage is going to be what? 20. Oops, can't see that. Voltage is going to be 20 volts. Boom. So that's pretty much it for the lecture that I'm going to be doing. I would definitely recommend you read over this chapter because these concepts are a little bit harder to kind of get a hold of. So, the more exposure you have to it, the easier it will be to understand. So yeah, definitely recommend, you read through the textbook or, just watch some YouTube videos. I may post one or two talking about electricity and et cetera. But the last thing I want to talk about now is labs 6 and 7, I think they are. Let me see. Yeah, labs 6 and 7. So lastly, I'm going to talk about lab 6 and 7. So lab 6 goes over electric charges. And electric fields. So the only thing about lab 6 is that you need Scotch tape, and you may or may not have Scotch tape at home. So I'm gonna try to briefly kind of describe what should be happening once you do the Scotch tape part of the experiment. So basically it says, get some Scotch tape and you're going to kind of put them together and strip them apart. So you have that piece there, and you have another piece here. Right? So you actually don't have to actually put these on a table. Let's say you're just holding these two pieces of tape. So I'm actually gonna hold them, do it this way. Something like that. So you have these two pieces of tape, and you basically have one sticky side taped onto the non-sticky side of the other tape. You have them like that and you just rip them apart. So basically what you're doing is, when you rip them apart, is you're stripping off some of the electrons from one of the tapes and it's going on to the other tape. So once I kind of rip this apart, the electrons on one of the tapes gets transferred to the other tape. So then I have two pieces of tape now that are oppositely charged. So now I have two pieces of tape that are oppositely charged, because when I ripped them off, one of the pieces of tape pulled some electrons off. So let's say this one, the blue one, pulled some of the electrons. So that means this blue one now is more negative because it took some electrons, making the red one more positive. All right, making the red one more positive. So now when you hold these two pieces of tape kind of next to each other, they're going to be attracted towards each other because, you know, opposites attract. And now let's say you do that experiment with another pair of tapes. So do it again with another pair of a piece of tape. Boom. So you rip these two apart and you rip these two apart. Now, instead of putting the two pieces of tape that you ripped apart together, now take one of these and one of these and bring them to each other. And then notice they're gonna repel. So if I take this one, and this one, they're gonna repel, right? Because we know like charges repel. Or if I take this one and this one, then they're also gonna repel. So if you do have Scotch tape at home, this is kind of cool to see, pretty easy to do. But if you don't, then this is kind of something that you would be seeing. And so Lab 6 also has a part 2 called John Travolta. I think that one's pretty easy. The only trick about it is you have to press tab on your keyboard. So you press tab and it's gonna highlight basically different part of John's body. So after you press tab a few times, it's gonna highlight either his feet or his hands. And then you kind of hit just left and right to continue with the lab. So remember to press tab for that part of the lab to highlight different parts of his body. All right. So I think the rest of the lab, you can kind of do that without any problems. And let's see, let me look at lab 7. And I think you should be good to go with lab 7 as well. All right then. Well, so that's it for this lecture. You know, again, good luck with the homework. Good luck with the lab. Yeah. Don't forget to read, study up. Good luck.